Hello everyone. What if just one extra bit could tell you that data got corrupted? A tiny bit but a huge job. That bit is called the parity bit. And today we will generate parity in ARM7 assembly on LPC2148. In this video we will understand why parity is needed, logic behind parity generation, ARM7 assembly code explanation, and how receiver checks for errors. When data travels through wires or communication channels, bits can accidentally change because of noise. For example, let this be our original data and this be our corrupted data. One wrong bit and data changes. So how does receiver know? That's when parity comes in. Parity simply checks how many ones are present. For example, consider this data. Number of ones equal to 4. Since 4 is even, we call it even parity. If count of ones is odd, then we call it as odd parity. Let's consider the sender side first. Sender first calculates parity of original data. For example, here we obtain 4 ones, so even parity. So sender adds a parity bit like this. Now this parity bit travels along with the data. On the receiver side, parity is calculated again on received data. Then receiver compares calculated parity with the received parity bit. If they match, data assumed correct. If they don't match, data corruption detected. The trick used in the code is that instead of counting ones manually, we use XOR because XOR of all bits directly gives parity. So, if the result is 0, it means even parity. Result is 1, then odd parity. First of all, let's check if this code has any errors. No errors, so we'll go ahead with debugging. The first thing you notice here is an assembler directive area which defines a section of memory to store this information. Parity is the name I have given to that section of memory. Code indicates the information here are nothing but actual ARM7 instructions. Read only indicates that this information should not be modified during runtime. Entry indicates where exactly execution starts. Execution starts at the very first label. Start, loop, stop are nothing but labels. End indicates the end of source file. In our first step, we are storing hexadecimal data 35 into register R0. To represent the data 35, we just need 8 bits. R1 is stored as 8 because we need to check 8 bits. Next, we have our parity accumulator in which our final result will be stored. After the execution of this particular code, if R2 has a value 0 in it, it means this particular data has even parity. If in case the value stored here is 1, it means it has odd parity. Let's store that value 0. Now, the very first task happening here is AND operation between R0 and 1. The reason for that is we are trying to extract the very last bit of this particular data and that value will be stored in R3. This particular content is now XORed with R2. Its initial value is 0. So whatever is the value in R3 gets retained in the register R2, which is nothing but 1. By performing this shift operation, that is shift to right, we are moving the next bit to LSB position. Let's perform the shift now. Okay, this is the answer we obtain. And next we are subtracting R1 by 1. And finally we check if Z flag is set as 0. If it is 0, we branch back to the loop. Else we break out of the loop. Our R1 is still 7, means 7 more bits are supposed to be checked and XORed. So let's see these steps getting repeated. So finally Z is now 1, because of which this loop is broken and we jump to this infinite loop. One thing to note here is parity is useful but not perfect. If one bit changes, parity usually detects it. But if 2-bit changes, parity may still remain same. So parity says this data looks correct even though the data is wrong. That's why parity can detect many errors but not all. That's all about this code.